Awesome. So I guess I should introduce myself. So I'm Nick Bishop. I'm a PhD student from the University of Southampton. I just finished my second year and I'm interested in strategic machine learning problems. And I'm going to talk to you today about a paper that me and my supervisors published at NeurIPS last year in 2020. And it's really about strategic linear regression problems, but I want to start from a more general setting about strategic machine learning in general and how to do better than the worst case assumption of adversarial machine learning we typically see when we're trying to relax this kind of i.i.d. data assumption that we typically make in supervised machine learning. So the paper title was Optimal Learning from Verified Training Data, and this was, again, as I said, co-authored with my two supervisors, Enrique Girding and Long Trantan, who's now at Warwick. So when we do machine learning, typically data is given to us by someone, right? We're not the people sampling directly from its distribution. And often these people are just strategic. They have their own motivations and their own goals in mind. So when we're learning, what we should really do is take into account these strategic behaviors. We shouldn't just ignore it when we select a model like we do when we typically assume that data is kind of i.i.d. distributed from some distribution of interest. So this kind of i.i.d. assumption is really kind of too strong for many realistic real-world settings. And there's been many attempts to relax it. And this is including this kind of adversarial assumption where you kind of assume the adversary is out to hinder your generalization power as much as possible, right? They meddle with input data so that you get classification wrong, you get labelings wrong, and so on. But this is also often way too pessimistic, right? You don't get data providers in general being like, I'm going to try and hurt you. My sole goal in life is to make sure that you can't generalize. Often these data providers will have goals which are completely orthogonal to the task you're doing, or just semi-related and not completely aligned. And we would like to have models that kind of take this nuance into account. And these are the kind of models I'm going to talk about today that try to find a middle ground for these kind of problems. So the plan for today is we're just going to start with the standard supervised machine learning setting, and we're going to point out some issues with this setting, and then we're going to move to a very kind of light model of what we can do to kind of model strategic behavior, and then we'll look at a very specific kind of bi-level optimization formalization for this model called stackable prediction games, and we'll look at the work we did in the NeurIPS paper where we kind of propose this polynomial time algorithm for this bi-level formalization, specifically for linear regression. So in general, bi-level optimization problems are NP hard, but what we'll see is for some of these stackable prediction games, which model this kind of nuance we're interested in, we can find global optima in polynomial time. So as I said, we'll start with the standard supervised machine learning setting, and typically you start with some kind of distribution, and we'll just denote this by D, and you draw some sample from it. And as I said before, you normally assume that this is independently and identically distributed with respect to the distribution D, and you get some sample of M data points, and then you pick a model denoted here by W dependent on the data points you sampled. And what you hope is that this model achieves low generalization error with respect to this original distribution. And as I discussed in the introduction, this i.i.d. assumption is kind of very strict, right? And you can think of plenty of examples in real life where this assumption doesn't hold. And really the kind of place where this breaks, which we're going to look at, is kind of where you're provided data by other people, and you can't guarantee the trustworthiness of this sample. You can't guarantee that this sample hasn't been meddled with in some way. Okay, and this isn't a problem, right, if you're doing some sort of physics experiment and you are conducting the experiment yourself, because you're essentially sampling directly from a distribution. But if you receive your data points from other people with other motivations, you can no longer make these guarantees, and you would like to have some learning guarantees for this kind of setting, or some model for this kind of setting. So really what we're doing is we're going from this setting of assuming that the data flow is directly from a distribution to a learner, and going from introducing a middleman in this process, which we're just going to denote as the data provider. And so this data provider is acting as a middleman between you and the distribution. And And these data providers will often be organizations or individuals. It might be something like Amazon Mechanical Turk, where you're crowdsourcing. It might be a business client who is submitting data. It might be a financial institution. It could be many things. And one thing to bear in mind is when you deploy machine learning systems in the real world, your decisions are going to have actionable consequences on these data providers. These are very likely going to be the people or individuals or organizations that are affected by the decisions you make with your machine learning model. So of course, these individuals are going to be motivated to manipulate their data in order to receive a better outcome in the future. Once you've chosen your model and once they realize the kind of decision-making rule you've decided upon, people are going to try to game the system. So the most kind of canonical example of this is spam email classification. And I'm sure if you're around in academics for like more than a month, you'll get one of these emails about your papers on archive, some journal, and like, we love your paper. You've never heard of a journal, and it seems very dodgy, and it's a spam email trying to get you to kind of submit your paper to this journal. And this is a kind of spam email I got the other day, and it got picked up in my spam filter. And it's funny because the very next day, I got an email from the exact same journal, completely different color format, completely different text, and it completely bypassed my spam filter. And this is kind of a perfect example where you can consider this spam filter as your machine learning model, and that spam email people, obviously their goal, their preferential outcome is not to be included in the spam inbox. Their preferential outcome is to be included in your mail inbox. So they are trying to kind of update their email formats, their text, to kind of bypass your decision rule. So once they are aware of what kind of spam filter you're using, you're kind of in this game-like process where people are going to try to manipulate their data to bypass your decision rule or get an outcome which is beneficial to them that might not be necessarily beneficial to you. Okay, so one way we can model this is we can kind of make a relaxed assumption where we're still sampling from some distribution. So this is before we've chosen a model, we're still sampling from some underlying distribution. But actually what happens at test time is our loss is computed with respect to some modified distribution, d tilde. And this kind of distribution represents how the distribution is modified by data providers, given their motivations and the model you've chosen. So of course, we need to assume some sort of relationship between d and d tilde that makes sense. And you get a lot of different models depending on how you assume these two distributions interact, right? So one obvious statement is if there's no relationship whatsoever, learning is impossible. I mean, the data is completely non-informative, right? It tells you nothing. If you just assume the distributions are the same, you recover this supervised machine learning setting we've already discussed. So we immediately see that this is more general. And of course, the most kind of famous model that takes this approach is the adversarial model, where we assume that the data provider is just trying to make your generalization as bad as possible. So they pick a distribution which hurts your loss and expectation as much as possible. And we normally place some sort of capability constraint on the adversary. So we normally say something like the distributions have to be bounded within some total variational distance of the original distribution. And this is just so you don't get some more powerful adversary, which again would make learning impossible. But again, this is very pessimistic, as we've already stated. Most data providers in real life aren't like this. They're not out to get you. And a perfect example of this is the spam email case. So spam emailers, on one hand, are an example of adversarial classification. They are trying to avoid being classified as spam when they are actually spam. But people who are honest and are just using the email service properly are the opposite. They are sending non-spam and they want it to be classified as non-spam. So if anything, their motivations align with you, and you would like to kind of represent that in some way in your model. And if you take an adversarial approach, you simply can't do this. You're also assuming that all truthful users of your platform are also out to get you, which they simply are not. If anything, they are cooperative. So like I said, this is kind of a pessimistic assumption. So really what we need is some more complicated model. So what we can do is we can define d tilde as the optimal value of an optimization problem, a solution of an optimization problem over all distributions. So here what I'm assuming is that the data provider has their own loss function, and this is given by G here. So they have some loss with respect to the model you've chosen and the data points they sample in expectation over the distribution they choose. So they're trying to minimize this expected loss, and this represents their incentives. So it might be if you're a truthful person on an email platform, this might correspond to making sure your email gets sent to someone's inbox. But they also have to trade this off with some inherent cost of manipulation, right? So manipulating the distribution inherently should have some cost, and this is the kind of cost you receive for making a forgery, right? It's the cost you receive for going into the process of making this forged distribution look like the real one. So this might be, the effort you put into creating a fake ID or so on and so forth. And we also include this hyperparameter gamma, which just represents the trade-off between the cost of changing the distribution from D to D bar in this case, as opposed to the benefit that gives you in terms of your overall loss. So you get this kind of scalarized optimization problem that gives you the solution to what D tilde will be if you pick W. And of course, if we set G to the zero mapping, we immediately just recover the supervised machine learning setting again, right? Because the learner really has no preference over what you classify its data points as, it could care less. And if we assume that your cost function is, sufficiently normal, like you'd expect, so it's a metric, it's always positive, all of these sort of things, then of course the best distribution to submit is just the original one, right? To incur no cost for manipulation whatsoever. So we immediately see that we recover the standard machine learning setting. Of course, if we take G to be minus L, where if you recall L was the loss of the learner, the loss function of the learner, then we immediately see that we get the adversarial machine learning setting, where instead of the cost being in terms of this total variation or distance constraint, the cost is in terms of this penalty term, where the penalty is dictated by the scaling you put on gamma, which again, I'm assuming is more than zero, like any sort of hyperparameter for regularization. So given this model, if the data provider had access to the distributions, they could actually compute the expected loss of their models, right? Because they could work out what the distribution would be, and then they could simply compute the expectation with respect to that specific distribution. So they could, you could do very well. You could immediately observe what your loss would be, and then simply you could just optimize over these losses to find the best one. And this gives you this bi-level optimization problem, where you're optimizing your model such that the expectation with respect to a distribution is minimized, where this distribution is the one induced by your data providers when they manipulate you. So this is what's referred to as a Stackelberg game, in the sense that it's a two-step game where I take an action, and then I'm assuming that the data providers are completely observing the model I choose, and then they are choosing the optimal way to manipulate me. So there's a very strong assumption here that the data provider is fully observant, right? And in some cases, this may be a little strong, right? You might, data providers, for example, might not be able to observe how insurance companies decide what your quote should be. But there are certain settings where institutions need to be transparent, so people will have full information about the model you choose. So this is worth bearing in mind. But of course, we can't actually do this optimization. Just like in standard machine learning, we don't have access to the distributions, so we can only estimate this empirically. Okay, and so all we're going to do is take an empirical approximation, and I'm going to cheat a little bit here and assume that this cost function can be rewritten in terms of the cost of pushing each individual data point to its manipulated version. So I'm assuming that manipulation consists of a data provider seeing an input example and moving it in the input space somewhere, and that has an extrinsic cost, and that the cost of the distribution is just the integration over these costs for each data point. So that I can rewrite this kind of as an empirical problem. Instead of having this cost function in terms of distributions, I now have it in terms of data points, but it's kind of a simple and intuitive translation to make. So now we've got this empirical version of a problem, and this kind of game is known as a Stackelberg prediction game, and it was first formulated by Buchner and Scheffer in 2011. And it's very, as you can see, it's very general. And they suggested an algorithm for this. So the difficulty of this problem is pi level, right? So they suggested an algorithm that basically reduces this problem to a single level problem. But the single level problem is non-convex. Okay, it's pretty horrible. But you can find local optima by doing sequential quadratic programming. So any standard non-convex optimization technique, assuming sufficient regularity conditions hold, will give you some sort of local optima for these kind of games. And in their paper, Buchner and Scheffer mostly looked at this kind of adversarial setting. So if you look at their paper, you'll see a lot of results regarding adversarial classification using this model. So for example, support vector machines, if you kind of take them into this adversarial model, often what you get is you get a support vector machine where the margin is uneven. So instead of a margin being uniform all the way across your kind of decision boundary, it kind of comes in and out depending on where your data is in data space and how that changes the cost function. And so it's quite interesting, but they never really looked at this more nuanced case that we're interested in of using it for more specific incentives. And it's also worth bearing in mind that this looks very similar to empirical risk minimization. Like, I mean, the objective is simply empirical risk, right? So if you just erase the argument and just assume that you had some distribution d tilde you're optimizing over, this would be identical to empirical risk. So you're kind of doing the strategic version of empirical risk minimization, which is very intuitive to do. Obviously you can start asking the question, like you would in normal machine learning contexts, is, well, is this a smart thing to do? Is this going to give you statistical guarantees? So typically you'd use some sort of complexity measure, right? Like VC dimension, Rademacher complexity, to kind of bound the generalization power of ERM. And this is the kind of theoretical justification for ERM in practice, that you have these nice complexity bounds on the generalization error. So we can kind of do the same here. So what we can do is we can say, well, in the supervised machine learning setting, we look at the complexity of our hypothesis class, right? Our hypothesis class H, right? And we define this kind of, if you're doing VC dimension, for example, you define the shattering coefficient with respect to this class, and then you compute an upper bound on this when this shattering coefficient is maximized to get the VC dimension. And we can do something similar here, but we need to be a bit careful because obviously when we pick a hypothesis, the data points are going to be modified. So instead of considering the complexity of this class, we can consider the computational, the VC dimension or the complexity of a modified hypothesis class, which for each hypothesis it contains HS, is just a modified version of the hypothesis from the base class of the models we're considering, where when we want to see how it classifies a point X, we actually want to look at how it classifies a manipulated data point X tilde, where X tilde is the kind of optimal manipulation given that H is chosen. And if you compute the kind of all the same kind of complexity, if you compute all the same kind of things you're familiar with in computational statistical learning that you're kind of familiar with, like shattering and VC dimension, you get all of these kind of strategic notions of these measures. And actually all the proofs still hold. If you can go through the entire proof, simply just replacing your base hypothesis class with this kind of strategic version of your hypothesis class, which also captures the strategic behavior of the adversary or the data provider. So you can get all the same kind of results. And there are a few papers out there now, recently this year, that kind of bound the complexity measures on these classes, right? So obviously these complexity generalization bounds are only actually useful if you can bound the VC dimension of these hypothesis sets. So obviously we have very nice results for stuff like hyperplane classifiers in non-strategic settings, but we don't really know anything about these kind of strategic hypothesis class, where we're kind of looking at the hypotheses after manipulation. And there are a few papers coming out now, and on the classification side, very few on the almost no work so far on the regression side. But these kind of bounds on the complexity are very, very sensitive to the assumptions you make. And it's still very much an open question about what kind of assumptions are correct. And really like what the right kind of complexity measure is to use. And in our paper, we don't focus on this question, we'll focus on the optimization question, but I just wanted to highlight the kind of point that there is a statistical motivation behind this, but there are also a lot of unanswered questions which I think are very interesting. So, what is the sample complexity of linear like hyperplane classifiers under strategic manipulation? What are the VC dimension of strategic VC dimension of, more complicated hypothesis classes? These are all kind of unanswered questions that I think are quite interesting and mark significant distributions that are yet to be made. So in terms of the optimization side, of course, if we go back to our bi-level optimization problem, we are left with this kind of this horrible bi-level optimization problem, right? So for simplicity, I'll assume that the loss function of the learner is convex. So basically anything in machine learning for neural networks. And I'll also actually assume G is convex, just to keep things simple. Even if you assume this, you're left with a convex-convex bi-level optimization problem, again, assuming C is also convex. But this is NP hard, right? This is known, very difficult problem, and it's actually harder than NP hard. And in fact, even if L and G are linear and C is linear, this problem is still NP hard. You can still easily find examples of linear bi-level programs that are just horrible. As I said, we kind of know that a lot of the machine problems we have are modeled in ways that have hidden structure or special structure that we can exploit. So we would hope in general that these kind of bi-level optimization problems based on machine learning problems kind of also have that special structure nested within them, and that this allows us to find faster algorithms. So this is really like the key idea behind our work, is that we're going to work with linear regression in a minute, and you'll see that the special structure of linear regression in particular allows us to find polynomial time algorithms for this kind of problem. And we believe that there might be polynomial time algorithms for other such problems, for other kind of machine learning models, but we didn't investigate this yet in the paper. So as I said, we kind of consider this Stackelberg game for linear regression. So we assume that our model is just simply a weight vector in dimension Rn. And we also assume that the learner has access to a small but verified training sample. And this training sample consists of tuples x, y, and z. And X is exactly what you'd expect. It's just a clean training example from the distribution of interest. Y is a label of interest to the learner. So this, is a standard label again, but you'd expect. And we also introduce this new data point Z, which is actually the label of interest to the data provider. So what we're going to assume in this game is that there's a label of interest to you that you want to be able to predict. But there's also a label of interest to the data provider that they want you to predict, right? So in the case of spam, if this was spam classification isn't a good example because it's a classification problem, but say you're an insurance, you're going to an insurance company to get your quote for your insurance. Your insurance company, you've got a true labeling in mind of how much they should charge you, but you also have a labeling of mind of what you deserve to pay, right? And you may disagree on this with the insurance company, and as a result, you may be a bit naughty and manipulate your data in order to get a lower quote. And so we're capturing this disagreement via the disagreement between the labels yi and zi. So one natural question to ask is, in reality, where does this verified training data set actually come from, right? Like we've just kind of assumed, we've just gone through all this effort to kind of argue that, data providers are going to manipulate you and blah, blah, blah. But in a lot of cases, there's ways of gathering verified training data sets. They can be very expensive, but you can gather a small amount of verified data that you can use for training. A classic example of this, again, is fraud detection for insurance companies. These insurance companies will have huge fraud detection teams that when they think something's iffy, they'll go out and they'll do a full inspection of all the information they can. And you can view this as some sort of certified and verified data from the original distribution. So I'm just trying to kind of here make the point that having access to a verified training sample isn't actually that strong of an assumption in a lot of instances in practice. So in many cases where strategic manipulation is possible, there's also a verification process. Typically, you don't want to use this verification process all the time, right? Because it's expensive, but you do have access to one. And if you need to pay a small fee to build a small training sample, you can do. So if we kind of plug in this linear regression model into our bi-level optimization problem, we get this bi-level optimization problem. So I'll take a little bit of time to describe exactly what's happened here. So we've assumed that the loss function here of a learner is simply the squared loss. And we've also assumed that the loss function of the data provider is also the squared loss. But the squared loss for the learner is with respect to y, and the squared loss of the data provider is with respect to z. And we've also modeled the cost function in terms of a squared distance between the input examples. So if you modify xi to x bar, the cost you pay is simply the squared distance between those two data points. So sorry, that shouldn't really be a bracket there. That should actually be a norm. That would make more sense. And of course, we still have our gamma term, which is kind of, again, capturing the trade-off between the cost you pay and the benefit you get to manipulating. So as I said, the aim of the data provider here is to manipulate each data point so that the learner predicts some output close to Zi, while the aim of a learner is to choose a model W which will perform well, given that the data provider will manipulate their data in response. And by perform well, I mean perform well with respect to yi. So we can just do some simple linear algebra on this problem to start with. So the first thing we can do immediately, which is completely obvious, is to simply compress everything into a matrix. So we can just take a matrix which is composed of the rows of the input data, as is normal in any kind of machine learning problem. And then you'll see that all of these arguments collapse into a single problem, which is just an argument of a matrix. And this is a kind of manipulated data matrix that we expect to see. And the reason these kind of arguments collapse is kind of obvious, is from the data provider's perspective, actually all they're doing is solving a one data point linear regression problem, right? So actually their model they're trying to learn is the manipulation, and the data they receive is the model, right? So they're just going to regress on X with respect to W to find the optimal manipulation. And they have this regularization term in terms of the cost. And while regularization is normally centered at 0, if you do like Tikhonov regularization, right? In this case, our regularization is centered at the original clean data point. So actually all these data manipulations just correspond to doing this kind of one data point regression. And this is the same for all, because all of the data providers have the same data point, i.e. W, all the arguments just compress into one. And so when you actually compute this argument, so obviously we want to get rid of this argument. It's kind of nasty in the constraint. We know bi-level problems are hard, so we'd like to get rid of it. You can just take the gradient and set it to 0, because if you note here that this is just convex in terms of x bar. And you get something that looks very similar to a pseudo-inverse. So this kind of matrix times some matrix plus I inverse. And this is kind of exactly what you would expect. And you can also see that gamma is popping up in kind of interesting places here. So you can kind of see that the smaller gamma is, the less of an effect the original data is having, which is kind of exactly what you'd expect, because obviously the smaller the cost is, the further you can manipulate from the original data point. So this kind of gamma is explicitly capturing here the trade-off between manipulation and cost of manipulation, benefit of manipulation and cost of manipulation. I, for one, don't like dealing with inverses. And my first instinct when I saw this was to simply just get rid of the inverse. And there's a well-known formula, I'm sure a lot of you are probably familiar with it, called the Sherman Morrison inverse formula. It's a more specific version of the matrix inversion lemma. It's used when you want to update the inverse of a rank 1. You want to update the inverse of a matrix once you add a rank 1 matrix to it. And so simply we're going to apply this formula here, but we're going to set A to I and U and V to W. And when you do this, you can then just simply plug it in to the equality. And then, of course, you can just substitute your formula for x tilde directly into your optimization problem. And you're going to end up with some single level optimization problem that looks like the one at the top of the screen. And this is kind of a very informative optimization problem, because it tells you exactly what kind of labels you're predicting if you look at it carefully enough. So you can see here that actually what you're predicting is a weighted combination of the label the data provider wants and the label you would predict if you were given the true data, right? So XW here is just the prediction you'd make if you were given the true data. Well, Z is the prediction the data provider wants, right? And you've got this weighting over both of these predictions where XW is weighted with 1 and ZWTW is weighted WTW, right? So what this is saying is, as you increase your norm, it gets easier to manipulate you. And this makes perfect sense, right? If you think of the scalar products, if W is very large, you only have to move X a small amount to change the prediction significantly. So what the learner has to deal with is they have to say, well, right, I have to pick a weight vector that does well on the clean data, but its norm can't be too big. If its norm is too big, then I'm just going to get pulled to Z, and I'm just going to get some error, or I'm just going to do exactly what the data provider wants. I'm just kind of stuck if I pick a really big W. So there's kind of some implicit regularization going on here. It's not quite as simple as you'd like. You'd like to think that you could just put a tick and off regularization penalty on this and just say, well, okay, I regularized the norm, I'm going to get to global optima. And this isn't quite true, and we'll see this in our empirical results. But we still kind of have problems with this optimization problem, right? One, it's still horribly non-convex, and it's actually quartic, and it can have multiple minima, it can have maxima, it can, yeah, it can be really nasty. But it's also fractional as well. So W here is appearing in the appearing in the denominator of this term. So it also has this fractional property to it, which is not nice to deal with. So the first thing that came to my mind again was, I don't like quartics. I would like to simplify them to something I know about, which is quadratics. So the first thing we did here was we made a variable substitution where we introduced this new variable alpha, and the alpha should be included in the min here. I've just forgot it. But we include this new variable alpha, which must be set equal to the squared norm of the weight vector. So as we've seen, the weight vector is a very important kind of measure for us that tells us how good a particular model can be. So we should probably include it as its own variable. And the immediate observation is this, of course, gets rid of any of the quadratic nature of the problem, right? Because we now just have linear terms inside the squared norm in terms of alpha and W. So we now completely get rid of this degree 4 polynomial problem that we had. But we are still left with this, this fractional program. And I should say here that all I've done is I've moved Y into the fraction and substituted in alpha, and then taken the denominator, since it's scalar, out of the norm. So this is how I got to this kind of formalization of this problem from here. Right. So we kind of need a way to solve these fractional problems. So I'm just going to very quickly run over some fractional programming techniques, which I was kind of surprised to see are not more commonplace in the kind of optimization and machine learning literature. So for now, just consider a fractional program, which is defined as some numerator function over some denominator function, where this denominator function is always positive, and we're optimizing over some compact set. We can construct a special function, which I will refer to as Dinkleback Functions, after the name of the author who originally kind of discovered these functions, which simply take real numbers to real numbers, which map any real number q to the minimum of nw minus q dw. So you can kind of think that what we're doing is we're subtracting a chunk of a denominator away from a numerator, and we're just changing the size of the chunk of a denominator we subtract. This function has a lot of remarkable properties, and they're actually quite simple to prove. I won't prove them here, but they're fairly simple to prove. The first is that this function is continuous and it's monotonically decreasing. And moreover, if W is in your is feasible, is a feasible point in your set, then FQ will be less than or equal to 0 if you simply just set Q to the evaluation of n over D at W. So immediately FQ can tell us when a point is feasible. So this is very useful. And the other thing that's very useful, which is perhaps the most useful thing about this function, is that a point Q star is only a root of this function if and only if Q star is an optimal value of the original fractional program. So that means if we can find a root of this fractional program, if we can find a root of this function, we can solve the original fractional program immediately, because we can just plug in Q star and find all our variables. So this is extremely useful. If we consider this Dinkleback program for our problem, it looks something like this, and it's not necessarily that useful, but it's worth pointing out at this point that this is simply just a quadratic program at this point. So it's much nicer than what we started with. And of course, as I just stated, the lemmas on the previous slide imply that if we can find a root of this, we can find the optimal value for our original problem, which is the Stackelberg prediction game we're interested in solving. And then once we have that, we can find the optimal model, right? One simple way of doing this is bisection search. So we know that this function is also strictly monotonically increasing. So what we can do is, if we can find a Q1 which is negative and a Q2 which is positive, we can just do bisection search and we'll converge to the root in linear time. So it's very nice and simple. I should state here that we pick bisection search instead of stuff like Newton's step method here that you might think might work for a very particular reason. And that's because an optimal value is only feasible if it's negative, right? So we need to make sure we end up on the negative side of the root, because obviously we're not going to converge exactly to the root. We're going to converge within some tolerance. So we want to have a Q which is close to the root, which is also negative when evaluated on F, because this means this optimal value is actually attainable, and we can find a W which attains this optimal value. But the kind of question is how do we pick this Q1 and Q2 such that they're positive and negative? Well, this is actually very easy. So for Q1, we can simply pick YTY. We know we must be able to achieve this loss because we can just pick the wave vector 0, and we achieve zero loss. We achieve YTY loss, right? We just predict everything as 0, and we achieve this kind of maximum loss. And we also know that our error is lower bounded by 0, so this is the best we can do. So why not just pick 0 as a lower bound? It's either going to be the optimal value or it's going to be less than that, and it's going to be positive. Okay, and so now we have this like really nice approach where actually all we'd have to do is do bisection search on F and we find our solution. Great, we're done, right? The problem here is that FQ is still kind of hard to evaluate, even though it's quadratic. It's got a quadratic equality in it, and yes, it might not necessarily be convex because of this minus Q plus 1 plus alpha squared term. So there's still a lot of problems here. But again, we can use some kind of a very familiar technique for those in control theory, which is the S procedure. So as I said before, this is simply just a quadratic program with a single quadratic constraint. So we can use a lemma, and this is known as the S lemma. You may have heard of it. And this is a specific version of the S lemma called the S lemma of equality. This is kind of a theorem which states that these two conditions are equivalent. So if we take two quadratic functions, I've mixed up my arguments here for Q and W, but they should all be W. But so if HW equals 0 implies FW is more than equal to 0 for all Wn, then we can always find this scalar value lambda, this Lagrange multiplier, if you like, such that FW plus lambda HW is also more than equal to 0 for all W in Rn. And this will be really useful to us because it will allow us to reformulate this QP as a semi-definite program. And then that's convex. We can use semi-definite programming techniques to solve it, and we're good. We can evaluate FQ. So even though this is kind of a very, very textbook, you can look this up, it's kind of quite nice and instructive to go through it once in a while. So I decided I'd go through it. So the first thing I'm going to do is I'm just going to clean up the notation a bit. So I'm going to let FW alpha equal to the first term in our objective value, our objective function, and I'm going to let HW alpha equal our constraint, where I've just moved everything to the left-hand side, so it's equal to 0. So it's in the form we need to apply the lemma. And then we're going to rewrite our optimization problem in this kind of epigraph form, where it's now a maximization problem over a new variable tau, which is just a real number. And we're going to say that if HW alpha is equal to 0, that is, if W alpha is feasible, then this implies FW alpha minus tau is more than or equal to 0. And so when you think about this optimization problem, what it's saying is that the optimal value you can set to tau is the minimum of FW alpha over all the W alphas such that HW alpha is equal to 0, right? So you can kind of intuitively see that the optimal value for tau is the minimum of this FG function you have up here, right? Because of this constraint which restricts you to the feasible set. And all we're going to do is apply the S lemma to this constraint now. So we're just going to say, right, we have this kind of, this is, if you recall, this is simply statement 1 in our lemma. So we're just going to convert that into statement 2, which is equivalent. So we're going to introduce a new parameter lambda, and we're going to say that we're going to find a maximum over tau such that FW alpha minus tau plus lambda times HW alpha is more than or equal to 0 for all W alpha in Rn. But if you think about it, this is just a semi-definite constraint, right? So this is saying for all W alpha, this quadratic has to be greater than or equal to 0. So this is equivalent to a semi-definite constraint on the matrix which represents this polynomial. So this is simply a semi-definite program. And it's in fact a very small semi-definite program. It's only got 2 variables. I mean, the dimension of the matrix you're checking for the semi-definite can be very large because it's going to contain your data matrix in it. But it's actually quite simple semi-definite program in terms of the variables. So yes, as I said, this is an SCP. So now we have a very complete method for solving our SPG for linear regression. We construct a function f. We then just perform bisection search on Q to find a root of f. And then we have a solution to fractional program of interest. And bear in mind here, we're using our SDP formulation to estimate f at each step of our bisection search, right? So our method therefore consists of solving a number of SDPs, and the number of SDPs you solve is going to be logarithmically dependent on YTY, right? Because the bracket you initially choose your bisection search is 0 and YTY. So, and I mean, if you include 1 over n, you can just assume this is the average magnitude of your data label. But so you're gonna solve a logarithmic number of MDPs dependent on the kind of magnitudes involved in your problem. And all of these SDPs can be solved in polynomial time. So you're going to get this kind of log polynomial time algorithm for solving your problem. This algorithm is very surprising, not so much just because it's polynomial, but also because it converges to global optima. We didn't mention local optima once when we were talking about these Dinkleback programs. They completely imply that the problem is solved, that you find the optimal value for the problem. So we don't even need to concern ourselves with local optima. We've somehow found a way to find some convexity through this S procedure in the problem, which is enough for us to solve the problem to global optima. And so this is an improvement on Bruckner and Scheffer's result immediately, in the sense that they can only guarantee convergence to local stationary points. So in this specific case, we can do much better. So if we now think about how we an example of this experiment in practice, you can kind of place yourself in a position of an insurance company, and you can say, well, I'm going to use linear regression to predict the future medical billings of my customers. And customers, of course, they might submit fraudulent data, so their projected medical billings are lower. And in this instance, we're going to assume that their medical billings, the medical billings they want to be predicted for, so that they receive a lower quote, is some sort of discount on their billing. So this should be a minus sign here, not a plus. I'm sorry for that. But so delta is like, if your medical billings is predicted at $1,000, you might set delta at 100 and say, I want my medical billings to be $100 lower than they actually are, because I think that's actually what they are, and that's fair. So this is the kind of model we're going to use in this insurance setting for ZI and YI. ZI is simply just a slightly discounted version of YI. But obviously you can think of much more complicated examples. And we ran some experiments. And so the green line here is our experiment. And the red line here is is ridge regression. And I should mention that ridge regression is optimal in the adversarial setting. So ridge regression, if you pick the right hyperparameter, it's very well known, but ridge regression is optimal for linear regression with manipulation penalized in squared norm. And we also tested Bruckner and Scheffer's kind of single level reformalization that I mentioned earlier. And we found that these it's very clear that these approaches of Bruckner and Scheffer and ridge regression are getting stuck in local optima, whereas we're not. And this can lead to great improvements in your performance. And I should mention here on the X, we're plotting the parameter gamma. So this is for kind of, if you recall, this is the hyperparameter we were using to control the trade-off. And you get this very natural curve, which you'd expect that as you put more weight on the cost function, you can do much better because manipulation is just much more expensive. So you get this kind of decay towards the kind of solution you would get if you were working on clean data because manipulating is just so expensive. And on both of these plots, we assume different values for delta. So in this case, delta is set to $100. So we just assume that people are trying to cut $100 off their billing. And on the right, we assume they're trying to cut $300 off. And we note that the more kind of severe this cutoff, this discount is, you do so much better. Like it's an even more pronounced improvement. So that's quite interesting as well. So as these become more misaligned, you actually, the difference between the local and global optima seem to be getting worse. So finding global optima becomes even more important. And just to contextualize these mean squared errors, because they really mean nothing, plotted as I have, these correspond to, on the left, to being about $45 better in terms of your predictions, and well over $150 better on the right. So you're really seeing some sort of significant improvement, which is, almost as big as the discount factor, or like half as big as the discount factor that the data manipulator is trying to get. So you're making significant improvements. So I think I'll finish there. But I just I'll summarize by just kind of saying that there's really a need for learning models which lie between the stochastic and adversarial settings. And it's really important, I think, in practice that we find these because strategic behavior is so much more nuanced than in practice. And if we take the strategic behavior into account, we now observed empirically that we can perform much better. So we should be doing this. And of course, SPGs are one tool for doing this, and we kind of outlined this, and they result in these bi-level optimization problems, which are very difficult. But for linear regression problems, we show that this is actually not too much of a problem, and we can solve this in polynomial time. And we can solve it globally, which is great. So I will skip this because I don't think it's actually that relevant. And I would just like to very, very quickly finish with some open questions, which I think are very interesting. So first of which is, do these kind of results hold for other machine learning algorithms, SVMs, right? These actually intuitively seem more complicated because they involve constraints. So if you had an SVM in your lower level problem, you're going to get these complementarity conditions, if you're familiar with the KKT conditions, which make the problem very much more difficult because the problem becomes heavily non-convex very quickly. And also, we kind of just took this verification process for granted, right? We didn't integrate it into our model at all. We just assumed we had it. But in reality, you're constantly updating your model, right? Consider the spam email classification setting. You're constantly updating your spam filter all the time. So actually, the data provider is reacting to your new models as they come online. And you always have the choice as you're learning online to go out and verify something, to pay a cost and go out and verify. And so there's a very natural question here to say, well, how should I verify? What data point should I verify? Which ones are going to help me learn the most? And this is kind of a selective sampling question, if you're familiar with that literature, or crowdsourcing kind of verification question, but for a very strategic setting, which I think is interesting. And I said this has natural connections to online settings. And also, I should mention that all the experiments we ran were under 10,000 data points. So obviously, we're solving this SDP at each time step. So this problem, this algorithm, even though it's polynomial time, really does not scale to high dimensions as you'd like classical kind of gradient descent first order methods. So it'd be interesting to see if there's kind of algorithms that are suited to high dimensions, and maybe these are not globally optimal, but maybe they have some kind of constant factor approximation. I think is an interesting direction. And also, as I mentioned, this open question of strategic hypothesis classes. how do you bound the subsample complexity of these things in practice? Like, what kind of techniques can you use to bound these? And what can we say about them in practice? And there's very little work on this so far, and I think it's very interesting, and there's a natural extension to the kind of pattern learning framework. Yeah, that's all I had to say. I've included a link to our paper.
Yeah, well, thanks a lot for a great talk. I'll stop the recording and then see if people have questions.